world of digital electronics, where logic meets innovation to power modern technology. This presentation, including all content, visuals, and materials, is the exclusive property of Pabana Semiconductor Private Limited. All rights are reserved. Unauthorized copying, reproduction, distribution, or disclosure of any part of this material, in any form or by any means, is strictly prohibited without prior written permission from Pabana Semiconductor Private Limited. The company name, logo, and all related marks are trademarks or registered trademarks of Pabana Semiconductor Private Limited. This document and its contents are confidential and intended solely for authorized individuals. Any unauthorized use, review, or sharing of this information may result in legal action. Copyright Pabana Semiconductor Private Limited. All rights reserved. This session, we are going to discuss arithmetic operations on the number system, like binary operations and hexadecimal operations. Binary addition works just like normal addition, but with only 2 digits, 0 and 1. The 4 basic rules are simple. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1, and 1 plus 1 equals 0, with a carry of 1. Start adding from the rightmost bit, just like in decimal. Remember, if a carry goes beyond the bit limit, it's called overflow. Binary addition is the foundation of all arithmetic operations inside digital circuits. Let's add 2 binary numbers, 0110 and 0011. Start from the rightmost bit. Step 1, add 0 plus 1 equals 1, no carry. Step 2, add 1 plus 1 equals 0 with a carry of 1. Step 3, move to the next bit. Add 1 plus 0 plus 1 carry. That gives 0 with a new carry of 1. Step 4, finally, add 0 plus 0 plus 1 carry. That gives 1. Now write the final result from left to right. 1, 0, 0, 1. So, 0110 plus 0011 equals 1001 in binary, which is 9 in decimal form. Let us take one more example. That is, add the numbers 15 and 1 in binary. First, write 15 in binary, 1111. Next, write 1 in binary, 0001. Now, let's add them step by step. Start from the rightmost bit. 1 plus 1 equals 10. That's 0, carry 1. Move to the next bit. 1 plus 1, carry, equals 10. That's 0, carry 1 again. Next bit, 1 plus 1, carry, equals 10. 0, carry 1. Next bit, 1 plus 1, carry, equals 10, 0, carry 1. Finally, bring down the carry 1 to the front. The result is 1000 in binary. Now, convert it back to decimal. 1000 equals 16. So, 15 plus 1 equals 16. Or in binary, 1111 plus 0001 equals 1000. Now, let's quickly review the fundamental rules of binary subtraction. These rules are the backbone for solving any binary subtraction problem. Rule 1. 0 minus 0 equals 0. Exactly the same as decimal. Nothing complicated here. Rule 2. 1 minus 0 equals 1. Just like decimal, subtracting 0 gives the same number back. Rule 3. 1 minus 1 equals 0. Again, same as decimal, 1 take away 1 gives 0. Rule 4. The important one. 0 minus 1 is not possible, so we must borrow. When we borrow from the next bit, that borrowed value becomes 2 in binary. So, 0 minus 1 becomes 2 minus 1, which gives us 1, and we mark borrow equals 1 for the next step. On the decimal side, you can compare it as 0 minus 1 is negative 1, which shows why we must borrow in binary. So remember, whenever you see 0 minus 1, borrowing is mandatory. These 4 rules form the core logic of all binary subtraction. Let's understand binary subtraction using the example 1011 minus 0110. We start subtracting from the least significant bit. Step 0. 1 minus 0 gives 1, and there is no borrow. Step 1. 1 minus 1 equals 0, again with no borrow. Step 2. Here we have 0 minus 1, which is not possible, so we borrow 1 from the next bit. After borrowing, the subtraction becomes 2 minus 1, resulting in 1, and we generate a borrow out. Step 3. Now the next bit becomes 1, but we already have a borrow coming in, so the calculation becomes 0 minus 0, giving 0. Collecting all bits from top to bottom, our final binary result is 0101, which equals 5 in decimal. So the subtraction 1011 minus 0110 results in 0101. Now, let's take a quick look at binary multiplication, one of the simplest operations in digital logic. The good news is, it follows the same basic behavior as decimal multiplication, and an AND gate, so it's super easy to remember. We only have 4 possible multiplication cases in binary. Case 1. 0 multiplied by 0 equals 0. Nothing times nothing, still nothing. Case 2. 0 multiplied by 1 equals 0. Whenever 0 is involved in multiplication, it dominates. Case 3. 1 multiplied by 0 also equals 0. Same idea. 0 pulls the result to 0. Case 4. The only special one. 1 multiplied by 1 equals 1. This is the only time we get a 1 as the output. So the golden rule is simple. If either bit is 0, the output is 0. Only when both bits are 1 does the result become 1. Think of it exactly like an AND gate. 1 and 1 gives 1. Otherwise, the result is always 0. These 4 rules form the foundation of all multi-bit binary multiplication you'll study next, like shift and add methods, partial products, and hardware multipliers. Multi-bit binary multiplication. Example, 1011 times 110 inches. Let's walk through the steps of multi-bit binary multiplication using the example 1011 multiplied by 1 zetron. First, we identify our numbers. The multiplicand is 1011, and the multiplier is 110. Step 1. We start by simply writing down the multiplicand 1011. This is the number we will repeatedly use for partial products. Step 2. We multiply the multiplicand by each bit of the multiplier, starting from the rightmost bit. Remember, in binary, multiplying by 0 gives 0, and multiplying by 1 gives the same number. This makes binary multiplication much simpler than decimal. Step 3. For each next bit of the multiplier, we shift the partial product to the left. Think of this shift as adding a 0 at the end, the same way we shift in decimal multiplication when moving to the tens or hundreds place. Step 4. Once we have all the partial products, we add them together to get the final answer. This addition step combines the shifted results to produce the full binary multiplication output. And that's the process. Write the multiplicand, multiply by each bit, shift for each position, and finally add all the partial products. That's how we perform multi-bit binary multiplication. Now, let's go deeper into our multi-bit binary multiplication example. We always start from the rightmost bit, so let's get into it. Let's look into the first partial product 1. The rightmost bit of the multiplier is 0. Multiplying 1011 by 0 gives us 000. So our first partial product is simply all zeros with no shift. Partial product 2. Middle bit 1. Next, we move to the middle bit, which is 1. Multiplying 1011 by 1 gives us 1011. But because this bit is in the second position, we shift this result left by 1 place. That makes the second partial product 10110. Partial product 3. Leftmost bit 2, 1. Now, we move to the leftmost bit of the multiplier, which is also 1. Again, Multiplying by 1 means we copy 1011. Because this is the third bit from the right, we shift left by 2 positions. This gives us the third partial product, 10110. Final step, add all partial products. Now we add all the partial products together. 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0. When we add them up, the final result becomes 1, 0, 0, 1, 1, 0. So, the multiplication 1, 0, 1, 1, 0 times 1, 1, 0 gives us 1, 0, 0, 1, 1, 0 in binary, which equals 66 in decimal. Let's move into binary division. And yes, it works almost exactly like the long division you learned in decimal. Just remember, in binary we only have 2 digits, 0 and 1, so our rules become super simple. Here are the core rules you must follow. 0 divided by 1 equals 0. 1 divided by 1 equals 1. But division by 0 is never allowed. In binary or decimal, division by 0 is always undefined. So when we perform binary long division, we simply check, can 1 go into this bit, or can 0 go into that bit? That's it. With these small rules, we can divide even big binary numbers easily. Let's move on to an example next. All right, students, let's dive into binary division. It works just like long division in decimal, but with only zeros and ones. Our example is 1011 divided by 10. Our dividend is 1011 and our divisor is 10. Let's solve it step by step. Step 1. Look at the first 2 bits of the dividend. 10. Can 10 divide into 10? Absolutely yes. So we write 1 in the quotient. Subtracting 10 from 10 gives us a remainder of 0, 0. Step 2. Now we bring down the next bit, which is 1. Our current number becomes 0, 1. Can 10 divide 0, 1? No, it's too small. So we place a 0 in the quotient and move on. Step 3. Bring down the next bit, another 1. Now we have 0, 1, 1. Can 10 divide into 11? Yes, it can. So we put 1 on the quotient. Subtract 10 from 11 and we get 0, 1. Step 4. Bring down the final bit, which is 0. Now we have 0, 1, 0. 10 can divide into 10, so once again, we write 1 in the quotient. Subtracting gives us 0, and we're done. Putting all quotient bits together, the final quotient is 1101, and the remainder is 0. So the division of 10110 divided by 10 equals 1101 in binary. This matches the decimal calculation. 22 divided by 2 equals 11. And that's your full binary long division. Clean, simple, and logical. Now let's understand binary subtraction, which is very similar to decimal subtraction but follows binary rules. Binary subtraction uses only 4 basic cases. 0 minus 0 gives 0. 1 minus 0 gives 1. 1 minus 1 gives 0. The important rule is 0 minus 1. This is not possible directly, so we must borrow from the next higher bit. When we borrow in binary, the borrowed value becomes 2, not 10 like in decimal. We always subtract from right to left, checking whether borrowing is required at each step. If borrowing occurs, it affects the next bit, just like in decimal subtraction. Binary subtraction is a fundamental operation used inside processors for arithmetic logic units, comparisons, and address calculations. Once you understand the borrow concept, binary subtraction becomes simple and predictable. Let's do a full step-by-step binary subtraction. 1011 minus 0110. We always subtract from right to left. Starting at the rightmost bit, 1 minus 0 gives 1. No borrow. Move 1 bit left. 1 minus 1 gives 0. Still no borrow. Next bit, we have 0 minus 1. That's not possible without borrowing, so we borrow from the next left bit. In binary, borrowing turns this 0 into 2. Now it becomes 2 minus 1, which gives 1, and we mark that we borrowed from the next bit. Now the leftmost bit was 1, but because we borrowed, it becomes 0. So we do 0 minus 0, which gives 0. Now read the result from left to right. 0, 1, 0, 1. So 1, 0, 1, 1 minus 0, 1, 1, 0 equals 0, 1, 0, 1, which is 5 in decimal. Now let's learn a very important subtraction technique called ones complement subtraction. This method is widely used in digital systems because it replaces subtraction with addition. Let's solve the example. 1011 minus 0101. Step 1. We start by taking the ones complement of the subtrahend. That simply means flipping every bit. So 0101 becomes 1010. Step 2. Now we add this ones complement to the minuend. We add 1011 plus 1010, which gives us 10101. Notice that extra 1 on the left. This is called the end-around carry. Step 3. In ones complement subtraction, we must add the end-around carry back to the result. So we take 0101, add 1, and we get 0110. So the final answer is 0110, which is 6 in decimal. That matches our expected result because 11 minus 5 equals 6. And that's the key idea of ones complement subtraction. Complement, add, and handle the end-around carry. Now let's understand how different subtraction combinations behave in binary using complement arithmetic. We'll look at 3 important cases: a minus b, b minus a, and negative a minus b. Case 1, a minus b. In the first case, a is greater than b, so we expect a positive result. We subtract b from a by taking the complement of b and adding it to a. If this addition produces an end-around carry, we add that carry back to the result. The presence of a carry tells us the answer is positive. So whenever you see a carry in complement subtraction, the result is positive. Case 2, b minus a. In the second case, b is smaller than a, so the result will be negative. Again, we take the complement of a and add it to b. This time, there is no end-around carry. When no carry is generated, it means the result is negative. To find the magnitude, we take the complement of the sum and we attach a negative sign. So remember, no carry means a negative result. Now let's talk about case 3, negative a minus b, written as negative a minus b. This is the most important case to understand when working with ones complement arithmetic. At first glance, it seems logical to represent negative a and then subtract b. But in ones complement, this approach has serious limitations. First limitation, limited number range. In ones complement, an n-bit number can represent values only from minus 2n minus 1 minus 1 to plus 2n minus 1 minus 1. For example, with 4 bits, the range is negative 7 to plus 7. If a is 5 and b is 3, their sum becomes 8, and since 8 is beyond the negative 7 to plus 7 range, ones complement fails to represent the correct value. Silent overflow occurs when the arithmetic result exceeds the representable range. The binary result still looks valid, but the numerical value is wrong. No error or warning is generated. Let's take an example of silent overflow in ones complement. We subtract 3 from negative 5, which should give negative 8. But negative 8 cannot be represented in 4-bit ones complement. The addition produces a binary value that looks valid, but it actually represents negative 2, not negative 8. Since no error is raised, the overflow happens silently. This is why ones complement arithmetic is unreliable for negative subtraction. The third limitation, known as the wraparound effect, occurs in ones complement arithmetic. Let me explain this based on an example. Negative a, negative b can be rewritten as negative a plus b. So here, we add a and b and then take ones complement to obtain the results. In our example, a equals 6 and b equals 3. We add 6 and 3, which mathematically results in 9. But in 4-bit 1's complement, the maximum positive value is 7. So when the sum exceeds this range, the arithmetic wraps around. The binary result becomes 1001, which actually represents -6. Notice how a large positive value suddenly turns into a negative number. This happens because the overflowed bits are discarded, and the remaining bits are misinterpreted. This wraparound behavior makes 1's complement arithmetic dangerous and unreliable. To resolve the issue, we must elevate the 4-bit operation to a 5-bit operation. With the implementation of the 5-bit mode, the outcomes will indeed fall within the 1's complement range. This serves as an example, and a similar problem may arise for any numbers. As digital designers, it is imperative that we recognize and analyze how the logic functions, as well as the limitations tied to altering the number of operational bits. So far, we have seen 3 limitations. This is the reason we use 2's complement approaches for binary subtractions. We will indeed discuss, elaborately, in the next slides, the fascinating concept of 2's complement. Now, let's solve -6 minus 3 using 2's complement, the method used in real processors. We first choose a safe bit width. Since the result is -9, we use 5 bits. We convert +6 and +3 into their 2's complement forms. -6 becomes 1110, and -3 becomes 1110. Now we simply add them together. After discarding the carry, the result is 1100, which represents -9. There's no end-around carry, no wraparound, and no silent overflow. This is exactly why 2's complement arithmetic is reliable and universally used. Now, let's compare this with 1's complement problems. Problem 1, limited number range. In 1's complement, a 4-bit system can represent values only from -7 to +7. So values like -8 or -9 cannot be represented at all. In 2's complement, the range becomes -8 to +7 for 4 bits, and -16 to +15 for 5 bits. This means all bit patterns are used and no values are wasted. Problem 2, silent overflow. In a 1's complement, overflow can occur silently. The binary output appears valid. However, the numeric value is incorrect. No error indication is generated. In 2's complement, overflow is detectable. By checking the sign bits of the operands and the result, the system can clearly identify when overflow happens. This makes arithmetic predictable and reliable. Problem 3. Wraparound effect. In 1's complement, when results exceed the valid range, the arithmetic wraps around, turning large positive numbers into small negative numbers or vice versa. In 2's complement, there is no wraparound confusion. Arithmetic progresses linearly, and any overflow is cleanly detected. Final takeaway. So to summarize, 1's complement suffers from limited range. It allows silent overflow, and it causes wraparound errors. 2's complement fixes all 3 by using the full binary range, providing clear overflow detection, and enabling simple, consistent arithmetic. That's why every modern computer system uses 2's complement arithmetic. Let's revisit hexadecimal numbers from 0 to 15, including the intriguing A to F symbols. And let's not forget about hexadecimal addition. The letters A, B, C, D, E, and F represent decimal values, 10 through 15. So in hexadecimal, A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. Now let's examine the fundamental rule for hexadecimal addition. We always add digits column by column, starting from the rightmost digit, just like decimal addition. If the sum of two hex digits is less than 16, we simply write the result directly in hexadecimal. However, if the sum is 16 or more, we subtract 16 from the sum and carry 1 to the next column. It's important to remember that the carry value in hexadecimal is always 1, just like in decimal arithmetic. The only difference is the base. Once you remember the hex digit values and the carry rule, hexadecimal addition becomes straightforward and intuitive. Let's look at a simple hexadecimal addition example where no carry is generated. We are adding 3a and 25. We always start from the rightmost digit. First, look at a plus 5. In hexadecimal, a represents 10. So 10 plus 5 equals 15, which is written as f in hexadecimal. Since the sum is less than 16, there is no carry. Now move to the next column. We add 3 plus 2, which gives us 5. So when we write the result from left to right, the final answer becomes 5f. This example shows that hexadecimal addition works just like decimal addition. As long as the sum is less than 16, we simply write the result and move on. Now let's look at a hexadecimal addition example that includes a carry. We are adding 7c and 8a. As always, we start from the rightmost digit. First, look at c plus a. In hexadecimal, c represents 12 and a represents 10. So 12 plus 10 equals 22 in decimal. Since 22 is greater than 16, we subtract 16 from it. 22 minus 16 gives us 6, and we carry 1 to the next column. Now, move to the left column. We add 7 plus 8, and don't forget the carry of 1. So 7 plus 8 plus 1 equals 16 in decimal. Again, 16 is equal to the base value. So we subtract 16. 16 minus 16 gives 0, and we generate another carry of 1. This carry becomes a new digit on the left. So the final hexadecimal result is 106. This example clearly shows how carries propagate in hexadecimal addition, just like in decimal, but with base 16. Now let's look at a multi-digit hexadecimal addition example. We are adding 9f3 and 2d9. As always, we begin from the rightmost column. First, we add 3 plus 9. That gives us 12 in decimal, which is written as c in hexadecimal. There is no carry here because the sum is less than 16. Now move to the next column. We add f and d. Remember, f is 15 and d is 13. So 15 plus 13 equals 28 in decimal. Since 28 is greater than 16, we subtract 16. 28 minus 16 gives c, and we carry 1 to the next column. Now move to the leftmost column. We add 9 plus 2 and include the carry of 1. So 9 plus 2 plus 1 equals 12, which is again written as c in hexadecimal. Putting all the digits together from left to right, the final hexadecimal result is CCC. This example shows how carries can propagate across multiple digits in hexadecimal addition. Now, let's understand 15's complement subtraction. This method is used in hexadecimal arithmetic. Hexadecimal is a base 16 number system. The highest hexadecimal digit is f, which represents 15 in decimal. The 15's complement of a hexadecimal digit is obtained by subtracting the digit from f. In other words, 15's complement equals f minus the digit. This operation flips the hexadecimal digit to its complementary value, similar to how 1's complement works in binary. So, why do we use 15's complement? The main advantage is that it allows us to perform subtraction using addition. Instead of building separate hardware for subtraction, we can use the same adder circuit for both addition and subtraction. This greatly simplifies hardware design and improves efficiency. Conceptually, 15's complement in hexadecimal plays the same role that 1's complement plays in binary arithmetic. So, remember? 15's complement converts subtraction into addition, making hexadecimal arithmetic simpler and more hardware-friendly. Let's Solve a hexadecimal subtraction using 15's complement. Our example is 7c minus 2a. First, we find the 15's complement of the subtrahend, which is 2a. In hexadecimal, the 15's complement is found by subtracting each digit from f. So f minus 2 gives d, and f minus a gives 5. That makes the 15's complement of 2a equal to d5. Next, we add this complement to the minuend. Adding 7c and d5 gives us 151. Now, we check for an end-around carry. Since there is a carry of 1, we add it back to the lower digits. 51 plus 1 becomes 52. So the final result of 7c minus 2a is 52 in hexadecimal. This example shows how 15's complement subtraction converts subtraction into addition. Quick reminder: carry present, result is positive. Add carry back. No carry, result is negative. Take 15's complement of sum. Now let's look at a 15's complement subtraction example that produces a negative result. We are subtracting 7c from 2a. Since the subtrahend is larger than the minuend, we expect a negative answer. First, we take the 15's complement of 7c. Subtracting each digit from f, we get 83. Next, we add this complement to the minuend. Adding 2a and 83 gives us ad. Now we check for an end-around carry. There is no carry, which tells us the result is negative. To find the magnitude, we take the 15's complement of ad, which gives us 52. So the final answer is minus 52 in hexadecimal. This example clearly shows how the absence of a carry indicates a negative result in 15's complement subtraction. Now let's look at 16's complement subtraction, which is the hexadecimal equivalent of 2's complement in binary. To find the 16's complement of a number, we first take the 15's complement and then add 1. Let's subtract 2a from 7c. We take the 16's complement of 2a, which is d6, and add it to 7c. The sum produces a carry, which we discard, leaving 52 as the final answer. Now let's reverse the order. 2a minus 7c. We take the 16's complement of 7c, add it to 2a, and this time no carry appears. That tells us the result is negative. To find the magnitude, we take the 16's complement of the sum, which again gives 52. So the final result is minus 52 hexadecimal. The key advantage of 16's complement is that there is no end-around carry, making arithmetic cleaner and more reliable than 15's complement. Kindly, please attempt all the practice problems. Moreover, include explanatory discussion comments for the solutions.